Hello everyone, today I will tell you how to solve the problem 10.7 and problem 10.12. And for problem 10.7, discuss the scattering of the plane wave of electromagnetic radiations by a non-permeable dielectric sphere of radius a and dielectric constant epsilon r. And problem A, by finding the field inside the sphere and matching to the incident plus scatter wave outside the sphere, determine without any restriction on Ka the multiple coefficient in the scatter wave. Define a suitable phase shift for this problem. And for problem B, consider a long wavelength limit. That means Ka is much smaller than 1, and determine explicitly the differential cross-section. Compare your result with those of section 10.1b. And for problem C, in the limit epsilon r goes to infinity, compare your result to those for a perfectly conducting sphere. And for problem A, we first need to expand our incident wave in the spherical basis, and the formula can be found in the equation 10.55. The incident wave the incident electric field is just the linear combination of the spherical Bessel functions and the x vector, where the x vector are the circular polarized vector with the m is equal to the plus minus 1, and the explicit definition of x vector can be found in the equation 9.119. And for the scatter wave with outgoing condition, the electric field and the magnetic field is the linear combination of the spherical Hankel function h1 here, and alpha and beta, and where the alpha and beta will be determined by the boundary conditions on the surface of the scatterer. In the outside region, the outside solution is the combination of incident wave and scatter wave. So the electric field in the outside region is just a combination of the incident wave JL plus the scatter wave spherical Hankel function, and so does the magnetic field. For the field inside in the inside region, inside the dielectric sphere, because our system have no source here, and we only have a modified dielectric constant, so this solution is just an ordinary spherical wave with a modified dielectric constant, and the impedance Z is equal to the Z naught divided by square root of epsilon r, where Z naught is the vacuum impedance. So the electric field in is just a linear combination of spherical Bessel functions and the circular polarized vector, where the AM and AE are the coefficients which need to be matched at the boundary. And in our problem, in these problems, because our system have no source, so on the surface of dielectric sphere R, which means R equal to A, we have the following four equations. The normal D field and the normal B field is continuous. The tangential E field and the tangential H field is continuous. And before we match these boundary conditions, there are some useful vector identities. The first one is the r hat dot the x vector is equal to 0, and the second one and the third one are just some vector identity when you rearrange the dot and cross product or you expand the double cross product, where the f are the spherical Bessel or spherical Hankel functions. And now we match the boundary conditions. For the normal B field continuous, we get AM times JL x prime is equal to JL plus 1/2 times alpha H1. For the tangential continuous tangential H field, we get these two equations. For normal D field, these boundary conditions are repeated, and for the tangential E field, the second boundary conditions are repeated. So there are two of them are redundant. We only have 4 equations in this problem, and we have 4 undetermined coefficients. So this is sufficient for us to solve our problem, where the k is equal to x is equal to ka, and the x prime is equal to k prime a, and which is equal to the square root epsilon r times x. And because we're only interested in the the multiple coefficient of scattering wave, so to find the multiple coefficients alpha and beta, we need to eliminate the coefficients am and ae. So to find the coefficients alpha, we first eliminate am and use the relation JL is equal to the H1 plus H2 divided by 2. The two boundary conditions related to the AM is these two. And to eliminate AM, we just divide the second equation by the first one. And after some algebra and simplification, you will get that the alpha plus 1 is equal to this expression. And so that same for the beta and the AE. After you divide the first equation to the second one, you will get the beta plus 1 is equal to these expressions, which is very similar with alpha, but differ from this epsilon r, the dielectric constant. Since H2 is a complex conjugate of H1, which means that the alpha and beta plus 1 is just equal to a complex number with the unit magnitude. We express this in terms of delta and delta prime here, where delta and delta prime are obey the following equations. The tangent delta is equal to this, and tangent delta prime is equal to this, where BL and BL prime are coefficients, which you can express in terms of the Bessel's function and its derivative with argument x prime. For problem B, we take the long wavelength limit, which means when the Ka is much smaller than 1. One can expect that only L equal to 1 is important, and we can approximate our spherical Bessel functions in the following form. The J1 is equal to this, and N1 is equal to this. With these expressions, we can expand our tangent delta 1 and tangent delta 1 prime into in terms of x and x prime. And after we rewrite x and x prime into Ka and epsilon r, we can find that the tangent delta 1 is proportional to the Ks power 5, and tangent delta 1 prime is proportional to the Ks power 3. So clearly the tangent delta 1 prime is greater than the tangent delta 1. And because we take the long wavelength limit, both tangent delta 1 and tangent delta 1 prime is a very small number, so it is approximately equal to delta 1 and delta 1 prime respectively. The multiple coefficients alpha and beta is just exponential 2i delta 1 minus 1 and exponential 2i delta 1 prime minus 1. And because delta and delta 1 are very small, so we can expand to the first order, and we will find the alpha plus minus 1 is proportional to the ks power 5. Beta plus minus 1 is proportional to the ks power 3. So the beta plus minus 1 is the dominant term in this long wavelength limit. The cross section d sigma d omega is equal to pi divided by 2k squared times times this square. And because only the beta plus minus 1 is dominant term, so we only take L equal to 1 and keep the beta terms here. And after we take the square of these things, we get our d sigma d omega is just equal to the 1/2 times k power 4 times s power 6 times these coefficients times 1 plus cosine squared theta. And this is the same as the equation 10.10, and hence this is agree with the dipole approximation perfectly. For perfect conductors, we take the limit epsilon r goes to infinity, and this limit implies that x prime is also goes to infinity. So the spherical Bessel function with the argument x prime can written in the asymptotic form. JL is approximate and can written in this form: sin x prime minus L pi divided by 2 divided by x prime. And with this asymptotic form, our BL and BL prime can also written in this asymptotic form. We find that the BL goes to infinity and BL prime will goes to minus 1. So we plug our BL and BL prime into our formula of tangent L and tangent delta L prime. We find the tangent delta L is just about JL divided by NLX, and tangent delta L prime is just about the derivative of xjl divided by derivative of x and L. And this expression is the same as the equation 10.168, which is exactly the perfect conductor result. For problem 10.12, a linearly polarized plane wave of amplitude E0 and wave number k is incident on a circular opening of radius a in an otherwise perfectly conducting flat screen. The incident wave vector makes an angle alpha with the normal to the screen. The polarization vector is perpendicular to the plane of incidence. A. Calculate the diffraction field and the power per unit solid angle transmitted through the opening. Use the vector Smith-Kirchhoff formula, the equation 10.101, with the assumption that the tangential electric field in the opening is the unperturbed incident field. For problem B, compare your result in part A with the standard scalar Kirchhoff approximation and with the result in the section 10.9 for polarization vector in the plane of incidence. For the problem A, by the Smith-Kirchhoff formula, the equation 10.101, the diffraction electric field can express in the following form, where the integration region is just the hole on the screen. And in this problem, our n is equal to the z directions. The incident wave vector k0 is equal to cosine alpha z plus sine alpha x. And our k vector is just use the ordinary spherical coordinate. Our incident incident electric field is E0 in the y direction, and the integrated region is parameterized by in the polar coordinate. So after we plug all the conditions in our diffraction electric fields, and we can take the exponential, the k0 hat minus k hat dot the exponent. We can express these things into these expressions with the trigonometric functions, and this the integral, after we use some formula about sine and cosine, we can change this integral into this form, and after the integration we will get this result is 2 pi times j0, where j is Bessel functions. And after this calculation, and the diffraction electric field is just the integration of j0 and after integrate j0 times rho, we get this is j1 kxa divided by kxa times a squared, and the H field is just k cross the electric field. So the power per solid angle is this formula, and we take the square root and we take the square of the electric field. We can get our power per solid angle is just expressed in this form with some angular dependence here, and the power incident on the whole is just the constant electric field is E0 squared times the area of the hole times the incident angle cosine alpha, which is just a projection. So our differential and our power per solid angle can written in this form: P in times some constant times this J1 divided by k c alpha times the angular dependence, and this J1 divided by k c alpha is the diffraction pattern in this problem. And for the problem 10.12b, the comparison, and for the polarization vector perpendicular the plane of incidence, which is just the problem A, the power per solid angle can express in this form. For the polarization vector in the plane, just in the plane of incidence, the power per solid angle can express in this form, which is just the case in the section 10.9. We can see when the incident angle is equal to 0, these two expression is just the same, and is almost the same, just different by this polarized angle. And for the scalar diffraction theory, the power per solid angle is written in the following form. We can see all these three results have the same diffraction pattern, but just a different angular dependence in the And this is today's problem.